So welcome to this fourth lecture devoted to model selection. So today I intend to continue the chapter on adaptive estimation, and more precisely, I would like to produce a lower bound which will show us that the log factors which appear in the complete variable selection situation are unavoidable in a minimax sense. So I remind you that we are still working with the white noise model, which is convenient to cover both finite dimensional and infinite dimensional situations. And last time we have seen that combining Birget's lemma, which is a multi-test lemma, and the computation of the relative entropy between points, white noise model experiments, it is possible to prove quite a general lower bound for some abstract quantity, some abstract subset T of the Hilbert space. And this lower bound depends on what? It depends on the fact that you are able to build nets. So the net here is a calligraphic C. And the quantities which are important in this net is the quantity delta, which says that the points are separated by some quantity, which is delta, small delta, and the diameter. So the idea here is that the nets that we shall try to build are such that capital delta and small delta are of the same order of magnitude. This is the idea. The nets which are interesting in this case are nets which are like that, with a diameter which is of the same order as the separation quantity, the width, small delta here. So if the diameter is not too large, and this not too large depends on the level of noise, on some constant kappa, which comes from Birget's lemma, and the log cardinality of the net, this is very important. Then you have a lower bound for the minimax risk, which is provided precisely up to constant by this width delta square. This is the general proposition that we have proved last time. So some comments about that. So there is a relationship, of course, between the size of T measured in terms of nets that you can put on it and the order of magnitude of this lower bound. So roughly speaking, what is happening is that you take a delta net, calligraphic C, and if this delta net can be built in a way that the diameter is of the same order of magnitude as the width of the net, then the lower bound, which comes from the proposition, is of order this width, delta. And you see that the best choice for delta is to saturate the constraint which is in the proposition. That is, you have the delta, which is such that delta square is of order epsilon square times the log of the cardinality of the net. So, of course, you have to realize that the width delta is also involved in this log cardinality because this net depends on delta. So this is some kind of implicit equation here, which gives you the order of magnitude of the lower bound. So here, the log cardinality plays a role of a dimension in some sense. This is what happens with the linear dimension of a linear model. Here you have a minimax risk, which is of order the dimension times epsilon square in this case. So this has the same flavor. The main difference is that here, in the general situation, the log cardinality depends on delta. In the linear case, you have a dimension which does not depend on delta, but in the general case, this new notion of dimension, in some sense, depends on delta. But it is the awful truth when you are leaving linearity and finite linear models. You have to face to this kind of problems. So we have applied this proposition starting from the discrete hypercube and extracting some convenient net. We were able to lower bound the minimax risk on some hypercube and then turn to the ellipsoids afterwards. So on the hypercubes, what we have proved is that the lower bound has this magnitude here. And you really see that the size of the hypercube does matter. If the radius here is larger than epsilon, then you get an order which corresponds to the linear situation. That is, it's not easier to estimate in this hypercube than in the whole space. This is what tells you the lower bound in this case. But on the contrary, if R is less than epsilon, then you have to take into account that you are in the hypercube and the order of magnitude is not the same as in the whole space. So this is a lesson which is provided by this proposition here. And then choosing the largest possible hypercube, we were able to prove this nice lower bound for the minimax risk on some ellipsoid. So it's possible to use this strategy to build lower bounds in small LP rather than the ellipsoids. You take LP ellipsoids rather than L2 ellipsoids. I do not enter into the details here. You can see how to do that in the notes. But now I prefer to come back to this complete variable selection situation and build lower bounds in order to see that there's a slowing value factor that we have seen appearing in the risk are completely unavoidable. And this is interesting because this shows you that the combinatorial properties of the list of models have an actual impact on the risk of estimation. And this is very important from my view. So let's remind the framework. We have a set of linearly independent functions here, phi j. They are in a finite number, but possibly this number is large. And the collection of models that we have considered in this case are the models which are spanned by subsets of this set of variables. And the complete variable selection situation is that we consider all the subsets of the initial set. So what we have seen in this case, that if you properly penalize the D square, then you can get a risk bound which has the following flavor, where you have this strange quantity here which appears, which is no longer exactly a log n, but it's a log n over D. And of course, you have a bias term, which is merely, oops, excuse me. The bias term is merely the infimum among the subsets with cardinality D of the distance square between the true and its orthogonal projection on the space which is spanned by the function phi j, which belongs to the set M. So you have this situation here, and in particular, if F belongs to if F, excuse me, is such that this bias is equal to 0, so what does it mean? It means that F belongs to some of the model SM which are such that the cardinality of M is equal to D. Then you have as a bound this D times the log factor appear here. So if you make this strange model appear, that is the union of the SM such that the cardinality of M is equal to D, the penalized estimator among this space here, if the true belongs to this space here, has a risk uniformly bounded by D times some constant, of course, times epsilon square, and times this slowly varying factor, which appears here. And of course, you ask yourself, is this slowly varying factor unavoidable, or can we remove it by finding a refinement of the refinement? Okay? So the answer, in fact, is no, you cannot remove this log n over d factor, and we can prove that by building a lower bound. So what we want to do is to prove the following lower bound. We want to prove that the minimax risk over the space capital SD, over the set capital SD, excuse me, is of order d epsilon square times this log n over d factor. And we shall actually prove a more precise result, which is the analog of the result that we have proved on hypercubes. If we introduce the union of hypercubes with dimension d that you can build with subsets of the initial sets 1, 2, up to capital N. So if you look at the union of these hypercubes here, the minimax risk over this union of hypercubes is lower bounded by a quantity which looks like what we had for a single hypercube, apart from the fact that you have again this factor here, this extra factor, which appears. Okay, so to do that, we shall use the same strategy as for usual hypercubes, apart from the fact that the Warschamoff-Gilbert lemma, which allowed us to extract a net from the discrete hypercube, we prove another lemma, which is the analog of the Warschamoff-Gilbert lemma. But you remember that the Warschamoff-Gilbert lemma was relying, excuse me, on the binomial. Here, we shall use the hypergeometric version of the Warschamoff-Gilbert lemma. So we take, again, a discrete situation. We take this set here, which is merely the sphere in 0, 1 to the power n. It is the sphere centered at 0 with radius d, which amounts to say that, of course, you perfectly know that 0, 1 to the power capital N, you can see it as the collection of subsets of, okay? So this set here is merely the collection of subsets with cardinality D of the set 1, 2 up to n, okay? So in this space, which is equipped with the Hamming distance, the hypergeometric lemma says that there exists some net, so some subsets capital theta, which has the following properties. In the one hand, the points are separated by a quantity which is of order D. More precisely, it is 2 times 1 minus alpha. Alpha is a given number between 0 and 1. This is what we have in the one hand. And on the other hand, the log cardinality of theta is of order of the log cardinality of the whole initial space, because you start from this space here, which also has a log cardinality of this order of magnitude. So this says that there are many points in the initial space that are separated by this quantity here. So this is the good news. And the constant ρ which appears depends on the two quantities that you have put in the machine at the starting point. That is, you have at the beginning taken two numbers, alpha and beta, between 0 and 1. And the separation depends on alpha, and the log cardinality depends on these two parameters at the same time, alpha and beta, through this explicit formula. And afterwards, we shall use it with alpha equal to 3/4 and beta equal to 1/3. And in this case, ρ would be larger than 1/5. So let's prove it. So let's see the proof of the hypergeometric lemma. So you will see that that the proof is very close to the proof of the Varchamov-Gilbert's lemma, but it is slightly more difficult from a technical point of view, but in spirit it is the same. So you start from this quantity here. Remember that it corresponds to the collection of subsets of 1 to n with cardinality equal to D. So you know that the cardinality of this quantity here, of this set, excuse me, this collection, is equal to the binomial coefficient. So we take a maximal set capital theta with the separation property, that is, the Hamming distance between points of theta are larger than 2 times 1 minus alpha d. So since you have taken a maximal set, you get a covering. The union of the balls centered at capital theta with radius 2, 1 minus alpha d are covering the initial collection. And of course, this implies that the binomial coefficient is less than the sum of the cardinality of the balls. And now we have to analyze the meaning of belonging to this ball here. So I come back to the interpretation of the space that we are working in as the collection of subsets of 1 to n. So let's see that. So we are working with sequences with points which are such that the number of the coordinates of these points in the product space which are equal to 1, this cardinality is equal to d by definition. So this means, I pretend that it means that for all x and y in the sphere, the Hamming distance can be computed in this way. You look at 2 times d minus the number of coordinates of x and y which are equal to 1 simultaneously. So why is it so? You just have to make a picture. Oops. So we are working with subsets of 1 to n. And here is the intersection between two sets and the part of each set which does not belong to the intersection. Okay? So here, this circle here corresponds to x, say, and this circle here corresponds to y. This is a subset of 1 to n, which corresponds to x, and this one corresponds to y. So what you see, of course, is that when you look at, you may say that this set corresponds to x, but you also may say that this set is a set that you call A, and this is a set that you call B. So, of course, when you look at the picture, you see that the intersection between A and B plus the part of A which is not in the intersection is equal to D. I just say that this set here has cardinality equal to D, and it is made of this part and this part. And of course, you have the same with B. So when you add these two quantities here, these two quantities are equal to 2 times D minus the cardinality of the intersection. Okay, I'm just adding these two equalities here. So we have, if I take this plus this, I get this. And of course, if I come back to the interpretation in terms of sequences, this is equal to the Hamming distance between x and y. Okay, so the Hamming distance between x and y is merely 2 times d minus the cardinality of the intersection, and this intersection is nothing else than the set of indices such that xi is equal to yi is equal to 1. This is the same. Okay, so I hope that I have convinced you that it is true that I can compute the Hamming distance in this way. And so the ball centered at the point x with radius 2 times 1 minus alpha d with respect to the Hamming distance is also the set of point y, which are such that the cardinality of the indices y such that xi is equal to yi is equal to 1 is larger than alpha d.
Monsieur, dans cet espace-là, si on définit une norme sur cet espace, est-ce que la norme est aussi identique que Rn? Ah, vous pouvez regarder mes messages. Merci.
Je ne comprends pas vraiment ta question. Là, on n'a pas de norme. On est dans un espace discret. Après, la distance de Hamming, tu peux toujours la considérer comme une norme 1 ou une norme 2. Comme tu es sur des points, comme tu es sur des suites qui valent 0 ou 1, tu peux toujours considérer que la distance de Hamming, c'est une norme 1 ou le carré d'une norme 2. C'est pareil. C'est ça ta question?
Oui. Vous pouvez regarder mes messages pendant la pause.
Oui, mais... OK, d'accord. Okay, so now let us come back to the proof by itself. Now, I do exactly the same as in the proof of the Varchamov-Gilbert lemma. That is, I equip this set with the uniform distribution. If I do that, then instead of making appear a binomial distribution, I make appear an hypergeometric distribution. More precisely, if I look at the number capital X, which becomes a random variable, so the number capital X of indices y such that xy, capital X of omega, such that xy is equal to omega y equal to 1. Okay. This number corresponds to a number of success when drawing d times without replacement in a population of capital N objects, among which D are favorable. So this means that you have a population here, a whole population. You have a subpopulation, which is given by X. So in terms of subsets, this is the set of indices such that xi is equal to 1. And you draw without replacement d times in this population. A success means that your draw is in this set, and you lose if you are outside the set. So looking at the number of success means that you are looking at drawings which are such that the set which you look at drawings which are in this set here. And so if you look at the distribution of X, X is no longer a binomial, it is hypergeometric with parameters capital D, corresponds to the size of the population. D, it is a number of drawings. This is a number of drawings. And D over N, which is a proportion of favorable points. So now, because of this remark here, the cardinality of theta, so all the balls have the same size, have the same cardinality, and the number, the cardinality of theta becomes larger than 1 over the probability that X is larger than alpha D. So you start from, oops, where is it? You start from this inequality here, which involves cardinalities. You notice that all these balls have the same cardinality. And this very cardinality corresponds, when you normalize it by n, by the binomial coefficients, it corresponds to a probability. It's a probability that X is larger than alpha D. So this means that at the end of the day, you have the cardinality of theta multiplied by the probability, which is larger than 1. So this means that the cardinality is larger than 1 over the probability, just as in the proof of Warshamov-Gilbert's lemma. And now there is a very beautiful argument that I learned a very, very long time ago. I learned it when I was beginning research, and I learned it from Percy Diaconis, who used it in a lecture that I had the opportunity to follow. And it's an argument which is due to Aldous. And this argument says that you may always realize an hypergeometric variable as a conditional expectation where y is a binomial. It's a corresponding binomial, that is, y is binomial with parameters d and d over n. So I just, of course, I do not intend to prove this, but I just give you the intuition behind this. When you look at the hypergeometric variable as a way to estimate the proportion, okay? If you compare drawing without replacement with drawing with replacement, which is what you do when you look at the binomial quantity. Of course, you have in mind that drawing without replacement is slightly better to estimate the proportion than drawing with replacement. So it is slightly more concentrated around the target, which is the proportion, than the binomial. And this is exactly what does this result says, because of course, when you can create the variable x as a conditional expectation starting from y, this means that in terms of any convex function, because of Jensen's inequality, the expectation of this convex function of x will be less than the corresponding expectation of the convex function of y. So this means that x is always better concentrated than y. Okay, this is the idea. And we shall use this result exactly by using Jensen's inequality. So by Jensen's inequality now, when I look at the moment generating function of x, its log, it is always less than the log of the moment generating function of y. So all what you know on the binomial holds for the hypergeometric. And so you can use Chernov's inequality. So the dual are, of course, going in the reverse sense. And when you look at Chernov's inequality, the probability that x is larger than alpha d is less than the exponential of minus the dual of the log moment generating function of the binomial. So that you can use Bennett's inequality. And Bennett's inequality tells you that if you look at the dual here, which is nothing else that the d times the rate function of Bernoulli variable with parameter d over n computed at alpha. This has to be larger than d square over n times the Poisson rate function, the Poisson with parameter 1, the centered Poisson with parameter 1. So the h function is as usual. And so when you look at the log cardinality of theta divided by capital D, it has to be larger than d over n h of alpha minus d over n divided by d over n. So this is a function of alpha and d over n. And now we have to analyze this function. This function is merely alpha log alpha over u minus alpha plus u. It is explicit. And the key is that if you divide this function of u by the log that you are looking at, then it is non-increasing on 0 alpha. You check this. And since it is non-increasing, this means that f alpha of u, as soon as u is less than beta alpha, this f alpha of u will be larger than f alpha of alpha beta over log of alpha beta times log of 1 over u. And this value which appears here f alpha of alpha beta over log of alpha beta is nothing else than the value rho, which is in the statement of the theorem. This is rho. And this is the end of the proof. You have proved the hypergeometric lemma. And so now, how to get the lower bound? On the union of hypercubes. It's quite easy. You combine the hypergeometric lemma with the general proposition that I have reminded you at the beginning of the lecture. So assume first that n is larger than 4d. then you use the hypergeometric lemma with alpha equal to 3/4, beta equal to 1/3. So alpha multiplied by beta is equal to 1/4. And the condition on D and N becomes N larger than 4D. So it's okay to apply the hypergeometric lemma. And so we combine with a general proposition, the general low bound. And this means that whatever the estimator, the maximal risk over the hypercube is larger than what? It's larger than R squared over 4 times D over 2, 1 minus kappa. So this 1 minus kappa here comes from the general proposition. This 1/4 comes also from the general proposition. And where does the R squared times D over 2 come from? It comes from the separation between points in the points of the union of hypercubes here, which corresponds to the discrete points capital theta. So you have this R square, which is involved because it appears as a radius in the hypercubes. And you have this D over 2 here, which corresponds to this D over 2. Oops. This D over 2 is just 2 times 1 minus alpha D. Okay, this gives you 1/4 times 2 is 1 over 2. So this is a combination between the hypergeometric lemma and the general proposition. And the constraint is that the diameter has to be smaller than something, that is the diameter delta square has to be less than 2 kappa epsilon square log the cardinality of theta. This comes from the general proposition. But here, remember that we are working in the hypercube, in the union of the hypercube. And remember that we are working with the discrete points which come from capital theta. And remember that, oops, let us come back to this. You have this computation here of the Hamming distance. Where is it? Here. And so the diameter is always less than 2D in the discrete hypercube. So at the end of the day, this gives you that delta square in the union of hypercubes is less than 2D, which comes from the discrete hypercube, times R square, which comes from the radius of the plane hypercubes in the Hilbert space. So that the constraint which is here holds a fortiori if 2dr square is less than 2 kappa epsilon square log cardinality of theta. So the two here cancel. And since the log cardinality of theta is larger than rho times d log of n over d, the constraint star is satisfied if d times r square is less than kappa rho d log n over d epsilon square. So the d here disappear, and you end up with a constraint on R, which is merely R square less than epsilon square times kappa times rho times the log factor. And rho is equal to 1/5 is okay. So now the proof is almost finished. So if this constraint here holds true, if this holds true, this is okay. If not, if R square is larger than epsilon square kappa rho log n over d, we do exactly what we have done for the hypercube. You use monotonicity, you use the fact that these hypercubes are plane hypercubes, and you can use the fact that the minimax risk, in this case, is always larger than the min-max risk for this border quantity. Use the preceding result with R0 square equal to the border quantity. And this gives you the infimum part of the lower bound. Okay? So the proof is finished. Proof is over if n is larger than 4D. And if it is not the case, if it happens that n is less than 4D, then you just use the fact that the log disappears in some sense. In this case, you do not care about the log. And the lower bound that you can use in this case is merely the lower bound for the hypercube. You just use a single hypercube, which is the hypercube that you get by putting the variables into order up to D. And it is enough. And we use the preceding, we use the lower bound for this hypercube. is enough. And the proof is over. So let's go back to the presentation here. We have proved the low bound, and now it's a good point and a good moment to make a break, coffee break, and after that we shall turn to the proof of the general Gaussian model selection theorem. I mean by general the fact that we are working with models which are no longer linear. So 5-minute break, and then we continue. So let's go on. With model selection for possibly nonlinear models. So we are still working with the white noise framework. And now the main issue, since we are working with models which are no longer linear, the main issue is to define a proper notion of dimension. Because of course, in the linear situation, the nice thing is that we have this notion of dimension, which is natural. For the general models, we have to define something which will play the role of a dimension. So this is the difficult part of the talk today, of this lecture, to understand this notion of dimension that we shall use. So instead of saying that we look at the log of the number of balls to cover the model, which would be a reasonable way of defining a dimension. We shall rather build on the modulus of continuity of the isonormal process. Why shall we do that? We shall do that in order to get as neater constants as possible, just because these constants are important for practical things, in fact. That is, you see that the cut k larger than 1, which appears in the linear case, we do want to see it appear again in the general framework, just not to lose when we come back to linear models on these constants. So rather than building on quantities like the metric entropy, for instance, which would be also a feasible way to deal with nonlinear models, we shall rather deal with a notion which is more involved and which takes into account the modulus of continuity of the isonormal process. The idea is that the smoother the process is, the smaller is the model. So let's see this in detail. As I mentioned, this is the difficult part of the lecture. So we consider some model, and we assume that there exists some regular version of the isonormal on this model. And we are controlling essentially the modulus of continuity of the isonormal process by some function phi m, which is, roughly speaking, concave. That is, you assume that the function phi m is continuous and non-decreasing on 0 plus infinity, and that it is such that the ratio phi m of t over t is non-increasing. So typically, a concave function which is equal to 0 at 0 has this property. And we assume that for all h in Sm, the expectation of the soup of the fluctuation of the isonormal process over this weight here is under control by phi m of t. So what is happening here? What is happening is that the important thing on this weight happened when the t square is of order of g minus h square here. So this means that in this case, the t square, which is at the denominator and at the numerator, cancel, and you are just looking at a quantity which looks like the fluctuation of the process at the scale t. And this is the idea. You are looking at phi m of t, which controls the fluctuation of the isonormal process at the scale t. So why do not we take it as the soup as j minus h less than t of the wj minus wh? We do not want to do that in this way, just to get as sharp constants as possible, because as you will see, this weight here will naturally be involved in the proof of the model selection theorem. So it's better to take this weight in this way. And at the end of the day, we define dm as the solution of the equation, which is here. And it's easy to see that this is meaningful because of the property of the function phi m. There always exists such a solution. Okay, so is it something which is completely fancy, or do we get the usual notion of dimension when we go back to the finite dimensional linear situation? The good news is that if Sm is linear with dimension dm, then we can take as a dimension the linear dimension. So let's see this immediately, because this is important, of course. So let's take a linear space with dimension d prime m to distinguish it with the notion that you have introduced. And let's see that it's possible to choose the function phi m in a way that the dm, which is defined from phi m, is equal to d prime m, as this will be true whatever the value of epsilon. So let's see this. So we take an orthonormal system in Sm, an orthonormal basis, and you use the fact that a squared plus b squared is larger than 2 times a times b. So this means that the initial soup here is upper bounded by this quantity here, just because the weight is heavier than the double product here. And after that, you just use linearity in order to expand this wj minus wh. So first of all, this soup becomes the same as when h is equal to 0, just by invariance by translation in the linear space. And afterwards, you expand j on the basis, and you use the linearity of w. So this means that what you make appear by doing this is merely the ratio between the sum of the beta j w phi j over the norm square of j, which is just the small L2 norm of the coefficients beta j. And of course, after that, this soup is exactly equal to the square root of the sum of the square of those guys here, just by Cauchy-Schwarz. And therefore, when you take the expectation, you use Jensen's inequality to say that the expectation of the square root is less than the square root of the expectation. And since these guys here are all normal variables, you get the square root of the linear dimension, d prime m, which appear here. So at the end, when you look at the quantity which is involved in the definition of phi m, you see that it is less than t square root of d prime m, and that you may take phi m of t equal to t square root of d prime m. And so the equation which defines dm becomes phi m of epsilon square root of dm equal epsilon dm. And you see that the epsilon cancel, and you end up with dm, which is equal to d prime m. So it's some kind of magic. When you go back to the linear situation, you did not lose anything. This pseudo dimension that you have introduced exactly corresponds to the linear dimension. Now that you have introduced this notion of dimension, the statement of the general model selection theorem will be exactly the same as in the linear case, apart from the fact that the minimal value of the least square criterion here is not explicitly computable as in the linear case. But apart from that, the statement will be exactly the same. So for convenience, we shall assume that the models are closed and convex. It is not essential. We can produce an even more general result than that, but at some stage, it's better to stick to something which is easier to prove. So I prefer to stick with closed and convex models. And in this case, of course, you have this notion of orthogonal projection, which is very convenient. And so the orthogonal projection onto the linear space has also a meaning here. It's the orthogonal projection in the usual sense in a Hilbert space on the closed and convex set Sm. And of course, the least square estimator is defined as the minimizer of the least square criterion on the model Sm. These things you already know because we have already talked about that. And now the statement of the theorem is exactly the same as in the linear case. The main difference is that here you no longer get the minus non-square of f at m because you do not know that it is the actual value of this minimal quantity. Actually, it's not its value at all in the general case. This is true in the linear situation, but not in the general case. So you take the minimal value as it is. And apart from that, the statement is the same with the pseudo dimension, which is involved instead of the dimension. And the new thing is that this pseudo dimension may depend on epsilon. Exactly as we have seen talking about lower bounds, that in the minimax lower bounds which appear in the white noise framework, the quantity which is involved in the lower bounds depends on the width of the net that you are considering. Here it's exactly the same idea. The notion of pseudo dimension that you have to consider has to depend on the scale, and the scale here is given by the level of noise of the white noise model. But apart from that, the statement is the same, the constraint on the penalty is the same, and the risk bound is the same. And since we have seen that this pseudo dimension corresponds to the linear dimension in the linear case, if we prove this theorem, it will imply that the linear version of the theorem holds true. Okay? So it is a strict generalization of the linear theorem. So the proof will essentially rely on the concentration theorem for suprema of Gaussian processes that we have seen. So I recall you the statement. I remind you the statement. So if you take some regular Gaussian process, then the soup concentrates around its expectation with a rate of concentration which is given by the maximal variance. This is the idea of the Gaussian concentration that we have proved together. And this is what we shall use as an essential tool. But we shall use also some other considerations to make the proof easier. It will be interesting to reduce the proof to the case where the target belongs to one of the models. And to do that, we shall use a very nice argument which is due to Andrew Barron, and which allows to compute the expectation under some distribution which is not too far from the initial one, if we do know that the initial variable, that the variable z that we are looking at under the initial probability has a sub-exponential tail. So if it is the case, you can explicitly compute or upper bound the expectation on under some other distribution by just taking this inequality here. And so the idea for us will be to make the proof under the model selection theorem under the assumption that f belongs to one given model, and then apply these results for a general f by using the preceding results on its orthogonal projection, and then go to the general case just by using Barron's lemma. I shall show you this into details after that. In order to apply Barron's lemma, we shall need again the computation of the relative entropy between two white noise experiments. And today I shall prove it. And I shall prove it by using Girsanov's formula that I shall not prove because it's a bit tedious to do it. So I prefer to stick on the statistical things today. So I shall prove this relationship between the relative entropy, but I shall admit the Girsanov formula. By the way, the Girsanov formula is proved in the notes. So if you are interested by seeing how to prove it, you can refer to the notes. So now I intend to prove Barron's lemma, and then I intend to prove that relative entropies between experiments of the white noise have this shape. We have already used it for low bounds, and now we shall use it to prove the Gaussian model selection theorem. So let's see the proof of Barron's lemma. So to prove Barron's lemma, we shall prove something which is slightly better, in fact, than the statement in Barron's lemma. We shall prove that the expectation is less than A plus the relative entropy of Q with respect to P plus the square root of 2 dq of P. And this implies the statement just by using, again, the fact that A plus B, excuse me, A square plus B square is larger than 2AB. Okay, so let's prove this now, this statement, this more precise statement. And to do that, we use again an old friend of us, that is the duality formula for entropy. This is our Swiss knife, and we use it under the following shape. We use that lambda times the expectation of z is less than the relative entropy of Q with respect to P plus the log of the moment generative function of Z. And of course, this implies that the expectation of Z under Q is less than the infimum over positive lambda of the relative entropy plus the log moment generative function over lambda. So this is the duality formula. And now what we have to do is to control the log of the moment generative function of Z. But we do know that Z has an exponential tail. So we know that the exponential of this log, that is the moment generative function, is equal to the integral of the tail of the exponential of Z and this is equal to the integral of the probability that Z is larger than the log of x to the power 1 over lambda. I have just taken the log under the probability. And now I just use the fact that the tail is less than exponential minus t, but of course the tail is also less than 1 because when t is too small, maybe this bound here is too crude. So I have to take this into account. And if I do that, I upper bound the integral by 1 infimum of ax to the power 1 over lambda dx. And this means that I have two different integral to compute. The first one is correspond to the situation where 1 is larger than that. And so I get a to the power lambda because this is precisely the value to which this is equal to this, plus the value of the integral, which is explicitly computable on the interval a to the power lambda infinity, that is a times lambda over lambda minus 1, x to the power lambda minus 1 over lambda, between a to the power lambda and infinity. And this is exactly equal to a to the power lambda times 1 plus lambda over 1 minus lambda, that is a to the power lambda over 1 minus lambda. So at the end of the day, when I look what happens for the log of the quantity, the log moment generating function is less than lambda log a minus log of 1 minus lambda. So this means that if I come back to the upper bound of the expectation of Z under Q, this will be less than the infimum over lambda positive of dqp over lambda plus this over lambda, which means log A minus log of 1 minus lambda over lambda. So minus log of 1 minus lambda. You can always upper bound it by lambda, which is the first term of the series when you expand this into series. And the second order term and the rest of the series, you can upper bound it by lambda square over 2, 1 minus lambda. This shape here is also an old friend of us, because we do know that under this shape, you have a nice computation of the dual of the log moment duality function. So let's go back to the upper bound here. We get expectation of z less than the infimum over lambda of dq over lambda plus 1 plus log A plus lambda square, lambda, excuse me, not lambda square, over 2, 1 minus lambda. And this now can be computed explicitly, because we get for free 1 plus log A, which is less than A, of course, and plus the infimum of this quantity, and this is explicitly computable. This is exactly equal to dqp plus the square root of 2 dqp. And we get the shape that we have that I have announced. We get this bound here, which was announced. And this is the end of the proof of Baron's lemma. So now we have to prove that the computation between that the computation of relative entropies between Gaussian white noise experiments is what we have announced. So make the computation of the relative entropies between Gaussian experiments. So by Gersanov's formula, we know the value of the density of the Gaussian experiment with respect to the experiment where we have 0 as a target function. So this means that this relative entropy here is equal to the integral of the density with respect to P0 of J times the log of the ratio of the two densities with respect to P0, and this has to be computed under P0. Now the log of the density no, it's F. If I compute it at Y, it is equal to 1 over epsilon square times Y of J minus Y of F plus F square over 2 minus J square over 2. This is by Kirsanov. This is just a change of variable. Okay, so this means that when I compute 2 epsilon square times the relative entropies, this has 2 terms. The first one comes from the random part of the formula here, and it is equal to 2 times the expectation of W epsilon times Wj minus Wf. So where does it come from? Here, when I look at Y, I have to integrate all these quantities with respect to P0. And P0 is the white noise with a signal which is equal to 0. So when the signal is equal to 0, this means that the difference between Yj and Yf is merely epsilon Wj minus Wf. And times the exponential of 1 over epsilon square times epsilon Wj minus J square over 2. And the second term comes from the deterministic part, that is, it is exactly F square minus J square. So what I have done here is that I have noticed that in the log here, there are 2 terms. I have a deterministic term and a random term. So the deterministic term, when I integrated against a density, it gives the constant. So the constant is merely F square minus J square if I have multiplied by 2 epsilon square. And the random part is given by that. Okay, so now what I have to do is to compute the first term. And to compute this first term, the trick is to introduce the orthogonal projection of F onto the linear span of J. So I introduce the normed J. I normalize it, the normalized J. I normalize it by dividing by its norm. So of course, J tilde is equal to 1. And I introduce F tilde, which is the orthogonal projection onto the linear span of F. And this is, of course, equal to F scalar product with J tilde times J tilde. Okay, so why did I do that? Just because I want to take benefits of the fact that when I look at WF minus WF tilde, then it is centered, of course, at expectation. And it is orthogonal. It is independent of Wj because F minus F tilde is orthogonal to J, and because you have the isonormal process. So this means that W is an isometry. So the variable W of F minus W of F tilde is Gaussian, is jointly Gaussian with Wj. And since it is orthogonal in L2, this means that it is independent. Okay? So now, this means that in the computation here, I can replace this by W of F tilde for free, just because if I write this as W minus W of F plus W of F minus W of F tilde, I see that the W of F minus W of tilde part will cancel because it is centered at expectation and independent of this variable here. So I see that the term number 1 is also equal to 2 times the expectation of epsilon times W, I use W of J tilde, times the norm, minus W of F tilde that I have substituted to W of F because of this orthogonality argument here, and times the exponential of 1 over epsilon square times epsilon, the norm of J, W of J tilde, minus J square over 2. This is what I get. And now W of J tilde is nothing else than, if I denote it by psi, is nothing else than a standard normal, because the G tilde has norm equal to 1. And so the computation of 1 here reduces to a computation of an expectation of a quantity which depends on a single standard normal variable. So this quantity is merely the following one. It is 2 times the expectation of epsilon times the norm of J times psi, which is the W of J tilde variable, times 1 minus F scalar product with J over J square, which comes from W of F tilde, because don't forget that F tilde is F scalar product with J tilde times J tilde. And of course, this is equal to F norm J times F no, excuse me, it's not norm of J, it's 1 over the norm square F scalar product with J times J. Okay, so we have this, which appears here, and times the exponential of norm J over epsilon xi, and times the exponential of minus the norm square of J over 2 epsilon square. And now it's almost finished, because here you have some constants. 1 is equal to 2 epsilon J 1 minus F scalar product with J over J square times exponential of minus J square over 2 epsilon square. This is a constant. And times the random part, which is merely the expectation of xi exponential of J over epsilon xi. And now, if you look at what it is, what is the value of the expectation of xi exponential of lambda xi? This is merely the derivative of the expectation of exponential lambda xi. And so this is the derivative of a quantity that we know perfectly, which is exponential of lambda square over lambda. So it is equal to lambda exponential of lambda square over 2. And so we just have now to finish the computation by plugging the value of this quantity here instead of that one here, and with the value of lambda, which is the norm of J over epsilon. And if we do that, the value of 1 becomes what? It becomes 2 epsilon norm J 1 minus F scalar product with J over J square, times the value of lambda, which is J norm J over epsilon, and times the exponentials, but the exponential cancel, because what we see up here, I put it explicitly, times the exponential of minus J square over 2 epsilon square, and times the exponential of J square over 2 epsilon square. So those guys here cancel, and this one cancels with this one. So at the end, 1 is merely equal to 2 times the norm of J square multiplied by 1 minus scalar product of F and J over J square. That is 2J square minus 2 times the scalar product between f and j. And so when I add 1 to 2, I get 2j squared minus 2fj. And what is 2? 2 is equal to f squared minus j squared plus f squared minus j squared. And this is, of course, equal to f minus j squared. Oof. And the proof is finished. Okay, so now I just want to explain how to use the Baron's lemma in order to prove the risk bound of the model selection theorem under the assumption that F belongs to some of the models. So let's explain that. So I pretend that it will be enough to prove the following statement. I pretend that it is enough to prove a tail bound which is exponential like that is except on a set with probability less than capital sigma exponential minus t. Then you have an upper bound for the L2 norm square between f and the selected estimator, which is controlled by a constant times the penalty plus epsilon square t. There is no bias here just because I assume that f belongs to Sm. Okay, so I pretend that it is enough to do that. Why? Because if I use Baron's lemma, I use it on the variable which is merely this guy here, to which I have subtracted this guy and renormalized by epsilon square times the constant. So if I renormalize this guy by epsilon square times the constant c prime k, and if I subtract this guy here, I just get that the tail of the variable z is, because of this inequality here, controlled in a way which allows me to use Baron's lemma. So I use Baron's lemma, and I get that under the true, under f, I have a bound which involves the constant which appears in the tail bound, that is capital sigma here, plus 1/2 which comes from the theorem, from Baron's lemma, and plus the 2 times the relative entropy between the Gaussian experiments between f and fm. And this is merely the 1 over epsilon square, which appears from the here, excuse me, it's just the fact that the experiments, when I compute this relative entropy here, is just epsilon 1 over 2 epsilon square f minus fm square. And so we have 2 over 2 which cancel, and we end up with this 1 over epsilon square times the bias. But this 1 over epsilon square is is not important because it will cancel by the normalization that now I put again by multiplying by epsilon square. And if I apply again by c prime k epsilon square, I get that this is less than the quantity that I wanted, that is a quantity which is announced in the theorem. Since after that, it remains to take the infimum, and the final result will follow. Okay, so this is a nice trick. Using Baran's lemma is a nice trick in order to make our life easier in the proof of the model selection theorem, because now we are allowed to assume that the true belongs to one of the models at the price that instead of proving a bounded expectation, you have to prove an exponential tail bound. But an exponential tail bound, we will get it for free by the concentration theorem. So this is what we are going to do right now. We are going to prove now the concentration theorem. And this will be the end of today's lecture. So now the proof of the model selection theorem. Let's go into this proof. So we assume, so we are given one reference model M. We assume that F does belong to Sm. Okay, so by definition, of M hat, we do know that the least square criterion computed at F hat M hat plus the penalty at M hat is less than L epsilon F hat M plus the penalty at M. This is by definition. And now, since F belongs to Sm, and since F at M is a least square estimator, which means that it is the minimizer of this quantity L epsilon of J when J belongs to Sm, this is also less than L epsilon computed at F plus the penalty of M. Now the L epsilon J criterion is equal to J square minus 2F scalar product with J minus 2 epsilon W of J. And therefore, if I add F square to L epsilon J, this is equal to F minus J square minus 2 epsilon W of J. And now, if I use this and if I plug this relationship into the inequality that I have here, this inequality becomes L epsilon.
The Beatles est un quatuor musical originaire de Liverpool.
Ça, c'est intéressant. Il y a Cyril qui me dit que les Beatles, c'est un groupe anglais, ce que je ne savais pas. Oui, au revoir Cyril. Attends, voilà. L epsilon of j minus L epsilon of f. So I rewrite this way, minus 2 epsilon W of j minus f. And so when I look at L epsilon of f hat m hat minus L epsilon of f, since I know that it is less than the penalty minus penalty of m hat, I get for free that the f at m hat minus f square is less than 2 epsilon times W of f at m hat minus W of f minus the penalty of m hat plus the penalty of m. So this is what we get for free. As soon as you use a penalized estimator, you get that for free, there is a control of the distance square between this estimator and the target, which is performed by this quantity here, which is given by this quantity here. And roughly speaking, the idea is that the penalty has to be heavy enough in order to kill this guy. And you will get it into the bound. The main difficulty is that you cannot expect this guy here to be brutally bounded by the penalty. This is not the way it works, because you have a natural scale here in the isonormal process, which is given by the distance between f and f at m hat. And so you have to renormalize the process before using a brutal uniform control. So this is what we intend to do now. So to take benefits of this natural inequality, we shall okay, do you hear me? It seems that you have, okay, the connection has been has crashed. So I have to see what happens now. Okay, so I have to share my screen again. Okay, that's one thing. And I have to check whether apparently the record is still working. So I continue. I go back to the proof. So this quantity y m prime square will be chosen later. I will have to choose this quantity afterwards. And now I introduced the weighted fluctuation of the isonormal process. This is the main part of the proof. I introduce the sup of the wj minus wf divided by the weight computed at j. And I look at the sup in the model Sm prime. And the basic inequality that we got before imply the distance computed at f hat m hat times v m hat minus the penalty at m hat plus the penalty at m. What did I do here? I just say that since I have taken the sup here, in the definition of Vm prime, when I look at the value which appears there, that is the value of W of n hat minus W of f, this quantity is always less than the sup Vm hat times the weight, because the weight is precisely the quantity that I have put here at the denominator of my quantity before taking the sup. So it's merely what I say here is that somebody at some point is less than the sup. So of course it is true. So this is what I do here, but it's important to do these things after having divided by a weight, because otherwise you would not be able to keep under control the fluctuation of the Gaussian process. So now precisely it's time to use concentration and a union bound. Since we do not know where is the hat, you have to control all these quantities at the same time. So this is what we are doing. For all m prime in K-graphic M, we use the fact that the probability that Vm prime is larger than this expectation plus the square root of 2Vm prime xm prime plus t is less than exponential minus xm prime minus t, where Vm prime is just the maximal variance of the Gaussian process involved, that is W of j minus W of f divided by the weight. So this is just Gaussian concentration. And of course, by using a union bound, I will be able to use all these controls at the same time. So this means that except on a set with probability less than the sum of the exponential minus xm prime, but this is capital sigma, times exponential minus t. For all m prime at the same time, the vm prime will be less than their expectations plus the square root of 2vm prime xm prime plus t. So now we have to control small vm prime and the expectation of vm prime. So small vm prime, it's easy. Small vm prime is the sup over j in Sm prime of the variance of the isonormal process. So it's, of course, the variance is the distance square over Wm prime of j. But the Wm prime weight is always larger than the product between the distance between f and j and ym prime. So that this Vm prime is always less than Ym prime to the power minus 2. Now we turn to the control of the expectation of Vm prime. And it is less than the sum of two terms. First, we look at the fluctuation of W between J and the orthogonal projection of F on the model Sm prime. Let's call this V, excuse me. Let's call this sup here. Under the expectation, let's call it Vm prime 1. And we have the fluctuation between the orthogonal projection and the value of the true. Positive part of it divided by the infimum of the weights. Here, there is some small thing to say. In this sup here, you are always sure that the sup is achieved for values which are non-negative values of the argument here, just because you know that j equal to fm prime is possible here. And so the heavier the weight, the smaller the quantity. When you look at W of fm prime minus W of f, of course, it is equal to what it is. So you cannot say that the heavier the weight, the smaller the quantity, if the quantity is negative. So you have to ensure that the quantity is non-negative. So you have to upper bound this by the positive part before using the fact that the heavier the weight, the smaller the quantity. And this guy here, I will call it Vm prime 2. So now I have to use the fact that the orthogonal projection is a contraction. This means that when I look at f m prime minus j with j belonging to Sm prime, I know that this quantity here is always less than f minus j. Because you have to see j as the orthogonal projection of itself. So this means that here you have the difference between two orthogonal projections, and so it is less than the distance between the points before taking the orthogonal projection. So this is true, and this implies that the weight 2 times W m prime of j is always larger than j minus fm prime norm square plus ym square. And therefore, we are in a position to use the dimensional assumption and the function phi m prime to control the expectation of v m prime 1. The expectation of v m prime 1 by our assumption will be less than y m prime minus square, y m prime to the power minus 2 times phi m prime of ym prime. This is our dimensional assumption. Now we shall choose ym prime later on, but we shall choose it in a way that it will be larger than epsilon square root of dm prime. The meaning of ym prime square is that it is, roughly speaking, the penalty. So the penalty is always larger than epsilon squared dm prime. So we can assume this, and we shall check it afterwards. And if we assume that, we may use the fact that the ratio phi m prime of t over t is non-increasing to ensure that the expectation of v m prime 1 will be less than y m prime to the power minus 1 time phi m prime of epsilon square root of dm prime over epsilon square root of dm prime. And now, by definition of dm prime, this quantity here is precisely equal to the square root of dm prime. And so at the end of the day, the expectation of Vm prime 1 is less than the square root of dm prime over y m prime. So this control is rather subtle, I confess. For the second term, it's much easier. You just have to use the fact that the infimum of the weight is larger than y m prime times f minus f m prime, because again f minus fm prime is always less than f minus j for all j, because of the definition of the projection. So you use first that the sum of the squares is larger than the double product first, and after that you use the fact that the distance between f and j is larger than the distance between f and fm prime. So that at the end of the day, the expectation of Vm prime 2 is less than 1 over ym prime, and times the expectation of a normalized normal variable, its positive part. So it's the expectation of a standard normal, its positive part. So it's something like 1 over the square root of 2 pi. So now let's see what it gives if we collect all these bounds. Collecting these bounds, we have that except on a set with probability less than capital sigma exponential minus t, for all m prime at the same time, Vm prime is less than y m prime to the power minus 1, which is which appears as a factor of all the other things. And the other things are the square root of dm prime, which comes from the Vm prime 1 term, plus the square root of 2xm prime, which comes from the variance factor term, and plus some remainder terms, which are simply the 1 over square root of 2 pi, which comes from the Vm prime 2 term, and plus the square root of 2t. And here I have just used the fact that the square root of xm prime plus t is less than the square root of xm prime plus the square root of t, just to make my life easier. And now you see that there is a very natural choice for ym prime. Now I have to take ym prime equal to this bracket, which appears here, times something which will make my Vm prime under control. So we choose Ym prime equals to the square root of k times epsilon times the bracket. I put it in two colors, so it will be more clear. This is this bracket, this blue bracket. Okay, so times this quantity, which is between these blue brackets. If I do that, except on a set with probability less than capital sigma exponential minus t, the epsilon times Vm hat will be less than 1 over the square root of k. If I choose Ym prime this way. And now I can come back to the inequality before. I come back to the Riesz bound. I get that the distance square is less than 1 over the square root of k times the distance square between f and fm hat square plus Ym hat square minus the penalty at m hat plus the penalty at m. And now this is the very point where you see the subtlety of the proof, because you see that this guy here, I recover it here. And this is the reason why I have to put a constant here, which is strictly larger than 1, in order to plug this term in on the left-hand side. Okay? So now the proof is almost finished. It remains to take into account some tedious algebra. We have to use several times the fact that a plus b square is less than 1 plus theta e square, a square, plus 1 over theta b square. In order to derive that the Ym prime square is less than k epsilon square times the square root of k times d square root of dm square root of 2xm prime square plus some remainder, which is 2 square root of k over square root of k minus 1 over 2 pi plus 2t. So it's a bit boring, but if you look at the value which is between the blue bracket, if the remainder term was not there, you would immediately see the essence of the proof, that is the y m prime square has to be of the order of the penalty in some sense. But since we have the remainder term and you have to take the square, here you will get a square which is of order close to the square of this one and not of this one. Okay, so this is what you use several times. And you get at the end this kind of evaluation on a y m prime square, which by essence it means that the penalty, because of the constraints that we have put on it, is larger than y m prime square over the square root of k minus some smaller term, which is taken into account by these guys here. And so at the end, the proof is almost finished now. We end up with the quantity square root of k minus 1 over square root of k times the distance square minus f and f hat m hat, which comes from the fact that I have put this guy from the right-hand side, I've put it on the left-hand side. And this is less than the penalty plus the remainder term, which is 2k epsilon square divided by square root of k minus 1 times 1 over 2 pi plus 2t. And this is true except on a set with probability less than capital sigma exponential t. And so you exactly get the tail bound that we wanted. And combining this with Baron's lemma finishes the proof. Okay, so it's a bit involved, I confess, but I hope that you have catch the main message, which is that the Gaussian concentration theorem directly influences the choice of the penalty, and the shape of the penalty which appears in this theorem comes from the Gaussian concentration theorem. Okay, so I stop here for the recording.